Okay, so picking up where we left off on the Slater's rules, um, these are the basic rules for what amount of shielding happens to a particular electron. So how do we apply these? This is the way that we can sort this out. Now, there are like other ways of organizing this information in your book. And that you can also use the chart that I gave you to look at it as well. But this is one way you can think about it. So this works particularly well if you have something in the transition metals or with a higher atomic number because you're going to have multiple levels you have to think about. So you're going to count all the electrons. So first of all, we're going to call the target electron the one that is being shielded, that we're talking about how much shielding is happening on this. So if I'm looking at, say, titanium, I might be talking about one of the 3d electrons, how much shielding is on that, or I could talk about one of the 4s electrons and how much shielding is on that. So if I'm looking at the um, the 3d electron, that is my target electron. So in titanium, there are two 3d electrons. So one of them is going to be my target electron, and the other one is also shielding it. Okay, so what we're going to do is we're going to count all the electrons in all the levels up to n minus 2. So if I'm talking about that 3d electron, n is going to be 3. So n minus 2 is 1. And so in level 1, there are only 2 electrons. And so I'm going to have separate rules for what's happening in level n minus 1 and level n. All right. So if it is a d electron, I'm going to go down to the bottom here. For a d electron, I'm going to count the 2 electrons that were in level 1. And then I'm going to look and say, okay, in level n minus 1, so level 2, I'm going to count all those as 1 as well. So I'm going to count the 2s and the 2p, that's 8 electrons. They also get multiplied by 1. Then I'm going to count the s and the p electrons that are in the same energy level. So remember, I have a 3d, so the 3s and the 3p, they are also going to get multiplied by 1. So everything is multiplied by 1 except that one other d electron, which is multiplied by 3.5. All right. I add up all those numbers, and that's how much shielding is going on. So let's look at an example. First, something that's easy. For oxygen, Z is equal to 8. So that's the nuclear charge. And we're looking for Z star, the effective nuclear charge. If I'm looking at a valence electron, N is equal to 2. So there aren't any electrons in N minus 2 because there's no such thing as level 0. So we can ignore that first rule. In N minus 1, that would be level 1, there are 2 electrons. So my rule for that, if I back up here, my rule for the S and the P, in level N minus 1, I multiply by 0.85. Okay, so I'm going to multiply those 2 electrons by 0.85. Then in level N, or level 2, every electron except for the one that I'm talking about is going to get multiplied by 0.35. So there are 6 electrons that are valence electrons, but an electron doesn't shield itself. So I'm going to multiply that 0.35 by 5 instead of 6. So I'm going to get 1.7, and that's for the level 1 electrons, and 1.75 for the level 2 electrons, which is 3.45. That is my S. That is how much shielding all the other electrons cause on one of the valence electrons. So the effective nuclear charge, Z, is going to be 8 minus that. So 8 is Z, the nuclear charge, 8 protons, minus 3.45. So that means in a neutral oxygen atom, the electrons aren't feeling the full 8. They're feeling a pull of about 4.55. Okay, so what if we have something that has a higher number of electrons? Okay, all right, so let's say we have selenium. So selenium is element 34. So that's our nuclear charge. Okay, so our rules say that we are going to look at all of the energy levels that are in level 1 to n minus 1. So let's see what the configuration is. It's going to be argon, 4s, 2, 3d, 10, 4s, 4. All right, so let's say I am looking at one of the, I'm sorry, 4p4. Sorry about that. Okay, let's say I want to know what is the shielding on one of these. So this is my target electron. So for the target electron, N is equal to 4. All right, so how many electrons are in levels 1 through 2? Well, that's going to be 10 electrons all the way up through neon. All right, so those get multiplied by 1, and I'm going to have 10. All right, then I look at how many electrons are in level n minus 1. That's going to be level 3. And so since I have all the d electrons there, that's going to be 18. So the 3s and the 3p are included in argon, and then I have 3d10. So that's 18 electrons. That is going to get multiplied by 0.85. And that's, if you plug it in, is going to be 15.3. And then finally, for n equals 4, I'm going to look and see that I have the 2s electrons, and then I have 3 p electrons that are not the one that I'm talking about. Okay, so there's 4 total, but it doesn't shield itself. So there's 3 plus 2 is 5 electrons in n equals 4 times 0.35. And that is going to give me 1.75. So I add all of those up, and that's going to give me 27.05. Might want to pause and make sure you get that same number. And then finally, if we want to know what is the Z effective, the effective nuclear charge on that electron, it is going to be Z, which is 34, minus 27.05, or an effective nuclear charge of 6.95. I also gave you a chart that looks like this. Okay, so on the side, we find the electron we were talking about. So we were talking about a 4p electron. And so this tells us that level 1 shields by 1, level 2 shields by 2, and level 3, the S and the P shield by 0.85, and the D shield by 0.85. All right. And then within the same block, it is 0.35. Okay, so that's how you would use that chart. All right. So the next question on the slide asks about nickel. So nickel has the configuration argon, 4s2, 3d8. Or you might think of that as neon, 3s2, 3p6. So this part is what is in argon, but we need to know about the energy level below. And then we need to know about the outside one. So 3d10, 4s2. All right. So that gets all of the threes together, makes it a little bit easier for us. Okay, we are going to compare the shielding on 2 different things. So we have the 4s electron versus the 3d electron. So on the 4s, 4 is our N. So levels 1 through N minus 2 is going to be levels 1 and 2, and that's going to be that neon core. Okay, so the neon core is going to be 10 electrons, and that's going to give us 10. And then we're going to look at level 3. Let me move this over here. And in level 3, I have the S, the P, and the D. So 2 plus 6 plus 10, that's 18. And because I'm looking at an S electron, this is going to be multiplied by 0.85. Okay, it's less for the S than for the D because remember they have some of their density close to the nucleus. All right, so they can kind of get inside the others a little bit. Okay, and so that's going to be the same as it was above, our 15.3. And then finally, in level 4, we only have one other electron, and that gets multiplied by 0.35. Okay, so we add all of these together, and we should get 25.65. And remember, that's our shielding. And then Z effective is going to be 28 minus 25.65. Okay, so the shielding on this makes the Z effective 2.35. Okay, that's how much of a pull that S electron feels. Now, if I look at my D electron, N minus 2 is just going to be the ones. So in level 1, I have 2 electrons. In N minus 1, that's level 2. So the N here is 3. So 3 minus 2 is 1. In level 2, I have the S and the P. So that's 8 electrons. But the rule for D electrons is that anything that's not in the same level is going to be a full 1. So we're looking at the 3D. So the 2s and the 2p that are a level behind it, they count as a full 1. And then we're also going to see even in the same level, the s and the p are going to count as a full 1. So this is going to be 2. This is going to be 8. And then in level 3, I have these and this. Okay, the S and the P count as a full 1. So I have 8 times 1. And then, so this is S and P. And then my 3D, well, I have, oops, this is not 10. Sorry about that. This is a 3D8. I have one electron that's in here that I'm talking about, so there are 7 other ones. So it's 7 times 0.35. All right, and again, if I'm looking at this chart for my 3D, everything except for other 3D electrons counts as a full 1. Okay, so that means I have 18 plus, need my calculator, 2.45. Okay, what about this 4s? Well, since n is higher, we are not even going to consider that when we are looking at the 3D electron. Okay, so this works out to 20.45. And that means that Z star is going to be 28 minus 20.45, which is equal to 7.55. All right, so a 3D electron is feeling a pull of 7.5, and a 4s electron is feeling a pull of 2 1/3. So when it comes time for something to be ionized, these are attracted to the nucleus less than these are. And that is why we lose our s electrons before we lose our d electrons. Okay, so as we look at this, then what do these rules predict about Z effective on 4s versus 3d? That's where we said Z effective was much larger for the 3d than it was for the 4s. And so because of that, our 4s electrons are lost first. Okay, pairing energy. Pairing energy is just that repulsion that is between our two electrons that are in the same orbital. All right. Remember that a negative energy is more stable and a positive energy is less stable. So pairing energy on an electron actually destabilizes it, kind of raises it up in energy. All right. Then I also get a certain amount of stability from having a half full orbital. Why is that? Because I can change the places of those electrons in degenerate orbitals, and the atom doesn't have a difference. So there are multiple ways for those electrons to be in there that are all of the same energy. That is called the exchange energy. So each pair of electrons that are degenerate and could exchange places without changing what the energy level of the whole atom is, that is exchange energy. So when we look at this chart, what it is showing us, what is it? It's showing us with these two lines that are parallel, but going at the same angle but separated. You'll see the -1/2 and the +1/2. So these two lines up here are the 3D orbitals and having all the same spin. So they're saying -1/2 first. All of those are the same energy level, but if I pair them up, having another electron in that same orbital is going to be a little bit higher energy. So flipping the spin and putting it a little bit higher up is higher energy. So rather than putting two electrons on the same line, they're saying there's actually a line down here for the first electron and a little bit higher up for the second electron. And we have the same thing going on with the S. So this pairing energy here is really small compared with the difference between the energy level of the S and the energy level of the D. So much so that as we go along with the different electrons or the uh, different energy levels of the orbitals based on the protons in the nucleus, um, the d orbitals are sinking down in energy because there's more protons, so there's more of an attraction. These orbitals get closer and closer to the nucleus, so do the s orbitals. But the d orbitals sink down in energy faster. They're not shielded very much. Okay, so down here at nickel, we've got a lot more stability in this nickel than we have in that second s electron there.